Hello, everyone. Welcome to the UFS webinar. This webinar is hosted by the NWS OSTI. The goal of this webinar series is to enhance communication and share advancements in all aspects of the UFS in both research and operational settings. My name is Stacy McKell, and I work with Yan Zhu, Program Manager at OSTI, to coordinate and deliver the webinar. Feel free to contact us if you have any comments and suggestions. Here are a few housekeeping items that I would like to bring to your attention. Just a moment. Okay. Due to the high number of attendees, you will be in listen-only mode during the event. You will not be able to unmute. If you have any questions now or during the event, please submit them via the question chat tab on your GoToWebinar toolbar on the right of your screen. The presentation lasts about 45 minutes, followed by questions and answers for 15 minutes. Please type your questions in the question box during the presentation. Today's presentation will be developing regional ocean modeling capabilities with MOM6 for use in UFS, presented by Dr. Enrique sorry to chop your name up, Curchitser at Rutgers University. Eric Chassignet will introduce the speaker. Okay. Before I get started, I would like to quickly show you how to sign up for the webinar notifications and how to view archived information. Go to the portal at ufscommunity.org. You're going to scroll down to the events section. You will see the webinar listed on the page. Archive information is available when you click UFS webinar series. Scroll down and there you will see the past webinars. You see the past webinars. Okay. Today's webinar will be recorded and made available on the UFS portal. Eric, the floor is all yours.
Well, thank you. Well, it's my great pleasure to introduce Enrique, who is a professor of climate and oceanography at Rutgers University. And at Rutgers, he leads the Earth System Modeling Laboratory, which focuses on the development and use of high-resolution coupled biophysical models. So that gives you an idea of his interest, research interests that are in understanding coastal physical biological systems and how they're forced by and contribute to the climate and weather systems. So his region of interest is working in the North Pacific, the Atlantic, and the through flow, Bering Sea, and the Arctic regions. So in addition, Professor Curchitser is the Editor-in-Chief for Progressive Oceanography and the Chair of the Intergovernmental North Pacific Marine Science Organization, or PICES. So now, Enrique, the floor is yours.
Thank you, Eric. So let me see. Can you see the presentation, please?
Right now we're seeing a white screen.
Yes.
Just a white screen?
Just a white screen.
Let's see.
Now we see the...
Now do you see the presentation? Okay.
Not in presentation mode.
Yeah, so I guess I cannot put it in presentation mode, right?
Yeah, you should be able to put it in full screen.
No. Okay.
Why does it become white? Strange.
It doesn't like that. Okay. I will just march. I will just march through it. Give me 1 second then. I don't know what it's doing. Sorry. All right. You can see that now?
Yes. except
right.
we're seeing a little bit the right-hand side. I think you're zooming in too much.
All right. I don't know what it's doing. All right. That works?
Yeah, I guess. Yeah.
Yeah. Sorry. Okay. We'll do it this way because I don't know exactly how to control that. All right. Good afternoon, everybody, and happy Earth Day. I'm going to talk today about a project that I have
excuse me, Enrique, I think maybe let Stacy to try. Right now, it's very small, the window for the main slides. Stacy, do you want to try on your end?
To run, let me see if
Run from your.
the presentation. Just a moment.
I don't know it's not, let me see.
You sent the presentation.
Is that better?
It's better this way.
Yeah.
Okay. Yeah, it's not letting me put it in presentation mode, so I'm just gonna do it this way.
Do you want me? I can do the display presentation mode. I can share my screen.
Hold on one second. I can
Trying to. That is better, bigger.
Does that work?
Yeah, that works. There it is.
Yes.
Okay. All right. So we'll do it this way. Good afternoon again. Happy Earth Day again. I'm going to talk today about where we are with a project that we share with Alistair Adcroft and Bob Holberg at GFDL and Avichal Mehra at EMC. And this is a project that was funded under UFS H-Fib, the Hurricane Forecast Improvement Plan. And the main goal that we have is to develop regional or limited area capabilities to use in UFS with using the MOM6, the GFDL MOM6 ocean circulation model. Under UFS, there is, as I just mentioned, H-Fib, so the Hurricane Forecast Improvement Plan. And under that, and in some of the plans for that, it calls for improved metrics and prediction for some of the hurricane forecasting capabilities, including intensity, path, and other metrics for tropical cyclones. And under that, there is the hurricane, so HAF, so the Hurricane Advancement Forecast System, or Advanced Forecast System, which is being developed to be able to incorporate in it a dynamical ocean component. UFS has picked GFDL's MOM6 as their next generation ocean model. And many of you may be aware that MOM6 is part of the GFDL climate model. It was developed as a global climate model. And so part of what we are trying to do is develop regional capabilities, or the capability to use it as a regional model as well, so that ultimately it could be incorporated into HAFs and contribute to the UFS tropical cyclone prediction efforts. The people that are directly funded or involved with this particular effort are here on the front page. However, I'd like to make sure that I mention there's many others that are contributing to this. Today, I'm going to talk I'm going to touch on things that the people that are mentioned here have contributed to. in particular Andrew Ross and Matt Harrison and Ralph Toussaint at GFDL, Kate Hedstrom and Rod Cermak, affiliated with the University of Alaska at Fairbanks, and then people in my lab that are working with me on this as well. It's been a transition, and hopefully we'll give you a sense of what all of that is. I'm relatively new to the UFS community, so I'm going to go over some background information here. Hopefully, I'm not repeating things. I really would like to do this in presentation mode. Oh well, that's the way it goes. No presentation mode. Motivation. Why are we interested in coastal regions? Well, coastal regions are susceptible to extreme weather events such as hurricanes and nor'easters here on our coast, on the East Coast, and storms in Alaska and Bering Sea and other places. 40% of the U.S. population lives in coastal regions, and there's an outsized contribution, economic contribution from industry, fisheries, tourism to the national economy. So ultimately, providing accurate forecasts is paramount to the safety of the population and the economic vitality of both the coastal regions and the national economy. And the point to really highlight here is that I guess we'll do it this way since I can't do it any other way, is that global ocean models often struggle, and I'm going to show a picture of that a little bit later in representing the weather, climate, and just general dynamics of coastal regions. Some of the understanding that we have is that some of it has to do with model resolution, but that's not always 100% of the reason, but that is a big part of the reason. So the challenge that we have is how do we represent a wide range of scales that matter to both the dynamics of coastal regions. So if you think of a tropical cyclone starting or the genesis of it in somewhere in the subtropical, let's say North Atlantic, and then makes its way to the coastal region, how do you represent all the scales that are relevant there? And as well, there's a wide variety of environments that on our shores that require sometimes different approaches to represent particular events. So you can think of the Hawaiian Islands being subtropical to the Arctic coastal regions where there could be ice covered part of the year or all of the year. So there's really many different environments that one has to account for. And if you're designing a global model, it may be more cumbersome or difficult to represent the details that could matter to an improved forecast in a particular region. I think that in the atmosphere, of course, that has been understood and known for a long time. And what we're trying to do here is to bring the ocean side of the equation up to speed. So there are many ways that you can think about the multi-scale problem and how to attack it. There's models, for example, like Department of Energy's MPAS model that uses an unstructured horizontal grid to represent, to have a global model that can then fine-tune its resolution or increase its resolution in particular areas of interest, whether they're coastal or otherwise. And those are popular techniques for dealing with multi-scale problems. They have their advantages and they have their complications as well, or their disadvantages. The way that we are thinking about it is to work towards using a common dynamical core for the model, in this case, the MOM6 ocean circulation model, and develop the capability within that to run limited area domains, so nesting, if you will, or regional models, if you will. And that will give us the capability to then represent both global or basin scale type of dynamics, and then try to downscale those to the particular area of interest with a common model. So let's look here at, see, do you see my arrow at all or not?
Yes, we see it.
Okay, all right. So, so here, talk a little bit about global ocean models. Here on the left, you have NCAR CCSM4. On the right, you have GFDL CM2.5. These are 1 degree global models that are part of their climate system. And these models there's a lot of experience in the community behind running these models. And you see some good things and you see some bad things. If you focus, for example, on the coastal regions, you see that there is these persistent biases on eastern boundary currents. So here's California Current, and Humboldt, and Benguela are areas of particular persistent biases in these models. And in western boundary currents, such as the Northwest Atlantic, and similarly in the Pacific, you see that there are problems. There are problems in these models. Again, these are about 1 degree ocean models. And similarly in the GFDL CM2.5 model, here I'm highlighting the Northwest Atlantic as an area that are persistent. It's kind of interesting to note that the biases in different models are showing up in coastal areas in similar places, right? So on the one hand, it's disheartening that after all these years, we haven't sorted this out. On the other hand, the patterns that you observe seem to be recognizable, right? The error patterns seem to be recognizable between the different models. So maybe there's some fundamental dynamics or physics that we are not representing well that would be common across the models, that when we finally crack that nut, we'll be able to improve these models. There's a lot that goes into these bias plots when you start looking at them, and people have written about this, I don't know if extensively, but periodically over the last decade or so. Some of it has to do with atmospheric resolution. That's one of the things that's been tried, to go from the classic 1 or 2 degree atmospheric models down to half or quarter degree global models. And when you do that, you often see improvements in some of these biases in some of the coastal regions, but not in all. So the atmospheric resolution hasn't been the only issue that has impacted this. There is work in increasing ocean resolution, and Eric, who kindly introduced me just before, has done some very nice work in the North Atlantic with an ocean-only model, a forced model, showing that as you increase the ocean resolution towards, I guess it was 2 kilometers, somewhere between 2 and 5 kilometers, you can actually, some of these features, you can do a much better representation in that particular case. This was a 2017 paper. They showed that the separation of the Gulf Stream can be significantly improved by increasing the ocean resolution. So this is a challenge that representing coastal regions has been with us for some time. And part of the work that we're trying to do is to work with increased resolution to at least to the point where we don't think that that's our last hurdle for improving these models. Here's a figure from a paper, again, assuming that I have a broad audience, that maybe not everybody thinking about the ocean. This is a time on the y-axis versus space on the x-axis from a recent paper we did. And these are common figures that you probably all have seen before, going back all the way to Stommel. So these phase figures, scale figures, and you see some propagating phenomena as presented here as a phase diagram, but also sort of some of the canonical ocean features, such as the overturning circulation, Anso cycles. And once you get down to smaller scales, you have Ekman dynamics, Langmuir cells, some instability processes, convection. The kinds of models that we're building right now are really aimed to sort of address the tens of meters to a few kilometer resolution dynamics. And then, of course, we always need to continue to parameterize the finer scales, the mixing scales, unless we're really running for short periods of time. And the question always, one of the questions that we always get is like, well, are you going to get there before computers become powerful enough that you can run global and not have to deal with the open boundary condition problem, which we'll talk about in a little bit. So this is a figure. It's getting a little bit dated, but I think it shows the point. So you can see this is the computational. So this is kind of a later take on Moore's law of how computer power is increasing. You see these green lines that this trend is getting steeper and steeper. So things are going faster than predicted at, let's say, in the early 60s here. Last I checked, we are still not at the exascale computing scale or ability. Once we get to the exascale, then our computers will have the ability to more or less mimic the amount of computations that a human brain, which evolution created about 1 million or so years ago. But right now, our computers are somewhere between a mouse and a monkey. This is important because if you pay attention to how much it costs you to run a global climate model now, and you, let's say, double the resolution now, and even if you were to give us a quantum computer tomorrow with, let's say, 10,000 times the power of the fastest computer now, it's really only going to buy you maybe an order of magnitude additional resolution in each direction for our ocean models. So I think that while I'm still employed for the next, hopefully, 15 or so years, so let's say 10 to 20 years, it's very unlikely that we will have computers that will be able to handle a 1 to 2 kilometer global ocean for any significant amounts of times. We can do those, of course, as a one-off demonstration that we can run them, and those have been done, and I'm sure more of those will be done in the near future. But as a matter of operations and for either weather or for climate, I really don't think that in the next decade or so we will be able to change the resolution significantly to change our understanding of the dynamics of the ocean with global models alone. So, so our goal remains then to develop regional models and try to link them as best as we can to the global simulations. So some of the Usf H-Fib goals are, of course, to reduce errors in forecast, as I mentioned earlier, in tropical cyclone tracks, intensity, and other quantities. And there was a working group that advocated for improved model resolution as a way to reduce those errors in forecasts, especially for tropical cyclones. And that was seen as a necessary and fundamental advancement to improve forecasting capabilities. And this is, I got this from a report from 2012. I believe that that report was at the time thinking mostly about the atmospheric resolution. What we are talking about here today is to carry that to, with the understanding that the ocean may be playing an important role in the dynamics and evolution of tropical cyclones. What we are trying to do is being able to bring the resolution of the ocean and the flexibility to run at whatever resolution we ultimately determine is important with that. And one of the ways that we're doing that is through regional models. There are high resolution global models, I should add that, and they tend to be typically at the 1/12 degree. So what we are talking about here is giving us the ability to keep increasing the resolution as needed. So the goal of our particular project here in red is, again, to address the H-Fib requirements for improved representation of storm parameters by developing and implementing regional high-resolution ocean modeling capacity within the MOM6, the GFDL MOM6 model, which is the model that was chosen to be the next generation model for halves. So here's a slide I took from a presentation of Bob Holberg from an NCAR talk he gave not too long ago. In case you're not familiar with MOM6, this is the one slide representation of it. And I'm going to just highlight the important things that matter to us here Today, it's a community ocean model that's really rooted in climate modeling. And this is an important point that we'll come back later to in the talk, because as we are taking this model to higher and higher resolutions, we have to develop new intuition of how to parameterize the subgrid scales and other components of the model that make it more adequate for the kinds of problems that we are thinking about. It is based on a structured sea grid, it's finite volume core, and it solves standard hydrostatic primitive equations for the ocean that are now common fare for all the global climate models and regional models, and has many capabilities from wetting and drying to representation of sea ice and ice shelves. One of the intriguing, not unique, but important characteristics of MOM6 is its arbitrary Lagrangian Eulerian, or so-called AL method, to represent the vertical coordinates. And here you have three different ways. You can represent the vertical coordinates as a density coordinate that's particularly useful if you're interested in tracking water masses for long periods of time, so very or negligible or no diapycnal mixing in this coordinate. You can use this to represent it as a terrain fallen coordinate that has been very popular in the coastal community because it allows you to retain your resolution over shallow areas like continental shelves, or as a z-coordinate or variations of z-coordinate that work well with sloping topography as well. That is a very popular coordinate system in climate models as well. The other thing is that you can actually mix this. I will show you later a case that is implemented in MOM6, taken from HICOM simulations that mixes density or sigma or raw coordinates with z coordinates or geopotential coordinates. The advantage of this method being Lagrangian is that it imposes no stability limit on your time step and resolution because of the very fine resolution that you could potentially achieve in the vertical. I believe that Bob Holberg has given a talk not that long ago in this seminar on MOM6 in particular. I don't want to dwell on that anymore, but just for sake of completeness, included this here today. So I'm going to start now talking a little bit about the work that we have been carrying out. And our goal in this project is really, in many ways, it's ambitious. We came in with some momentum of that we were already thinking about this at some point over coffee, or maybe it was beers, I forget at this point. We sat around and said, hey, wouldn't it be nice to take MOM6 and all the good things that it has and turn it into a regional model that we could run at high resolutions for coastal problems, which has been my area of interest for some years now. And one thing led to another, and we started playing around with this. And what we, again, hope to do in this project is to finish the development of this regional model, these new regional capabilities within MOM6, and to start to implement them in the, let's say, the Northwest Atlantic or in the North Atlantic for hurricane forecasting purposes. So given our experience, a couple of decades of experience running regional models, it gave us a clean slate to start thinking about how we want to do this. And the first realization was because we are interested in the multi-scale problem where we want to link the basin scale or even the global scale down to coastal systems, that both the global model or the basin scale model and the local, let's call it the coastal model, both of those are going to need to be able to handle the exchange of information. So if you think of the, let's say the North Atlantic basin as the parent model or the parent grid, and the Northwest Atlantic as your child grid, we want to be able to take information from the parent grid and take it down to the child grid. But we are also thinking that in the future it might be interesting to be able to then take that information. Let's say we have an improved Gulf Stream path at higher resolution. Why not feed that back to the basin scale model? So we designed, right? So how do you build a regional model? You code up some open boundary conditions. But what we did in our design philosophy was to, rather than think of it as a boundary condition that's actually on the boundary of your grid, we designed these segments that you can put anywhere. And you can think of them as just it's like lines where you are solving a different set of equations, whether they are your radiation conditions or whatever different physics or dynamics you think you may want to implement on a particular line, right? And they call that your boundary segments. So again, this was done with the ultimate goal of being able to pass information from a parent basin scale grid down to a region and eventually upscale the upscaling problem again. As was briefly mentioned a couple of slides ago, MOM6 is built on the Arakawa Sea grid. So the information that we need to pass through the boundaries, through these segments, are the free surface, the normal velocity. Because of the vector invariant formulation of MOM6, there's also a need to pass in tangential velocity, and of course, tracers, temperature, salinity, and if you are running biogeochemistry, there's going to be a need to pass those through the boundary as well. And there is, in the AL world, layer thickness. This is a little bit more complicated. We have something implemented for it now, and probably room to improve this in some future implementations. So what have we done so far? We have coded up open boundary conditions in MOM6. And these are the options that are currently available to you if you get your hands on the code to try. We have so-called simple or clamped boundary conditions. This is where you just simply take a value and impose it without any additional dynamics, and the value can be from a parent, from your parent grid, or it could be, if it's collocated, that could be all you may need to do, or it could be from some observations or whatever the case may be. You just simply tell it what it is. You can get a little more sophisticated by saying, for example, you have a zero gradient between your outside information and inside information. We have implemented flatter boundary conditions for the barotropic mode, and I'll show you what that equation looks like in a couple of slides. We have radiation boundary conditions for the baroclinic mode that all date back to Orlansky, and variations of that, whether they're oblique or the ability to deal with information coming in or out of the particular domain with different timescales. So basically, you have boundary conditions for the barotropic and baroclinic modes and variations thereof. For the tangential velocity, so these are, for those of you that are familiar with regional models such as ROMS, the Regional Ocean Modeling System, this is a standard suite of boundary conditions that are available. Again, because of the need for the tangential velocity, going back to the formulation of the equations that are used in MOM6, we had to implement so strain or vorticity equations, so tangential velocity, which again can be implemented as a zero gradient condition, or radiation of the components of the vorticity that are appropriate for that boundary. Whether it's north-south or east-west, you will take a different component of that, of course. And again, you can use this to compute it from velocities from some file, or you can radiate them in if you happen to have them stored, let's say, from parent grid simulation that you do. The barotropic mode based on flatter, this is it works really, really well. We have lots of experience with this. It relies on so the boundary condition is evaluated using the barotropic mode outside of your domain, so your boundary condition, and the free surface side, which is related to the barotropic velocity through the conservation of mass equation. This works really well. No issues here. The problems come when you, so the art of the open boundary condition really emerges with the implementation of the baroclinic mode, which is based on your landscape radiation. And one could give a very long talk about this topic in particular. We are using oblique radiation, but the problem really arises is that, to summarize it quickly, is that we have a parabolic system that we don't really know what the characteristics are. So we are guessing them in some sense, or we are not guessing, approximating them, guesstimating them, and they're never exactly precise. So,
excuse me.
Yeah.
Enrique, sorry to interrupt. You have to note, sorry if we forgot to, maybe the seminar, webinar usually lasts about 45 minutes.
Yeah.
I see you have 40 slides. You may want to, speed up. Yeah, thank you.
Will do. Will do. So, okay, so we introduced some errors through this, and this is where the art of implementing these conditions are. Yeah. Okay, more boundary conditions. We have boundary conditions for tracers, temperature and salinity, as well as for biogeochemistry recently that have been implemented at GFDL. And as I mentioned earlier, for layer thickness used in the continuity and Coriolis computations. Right now they're set to no gradient with the AL vertical coordinate. That's a little bit more difficult, but this is a place where we may ultimately spend a little bit more time trying to improve that. Tidal forcing, one of the MOM6 had implemented in that self-attraction and tidal potential. What we have done, and this is Andrew Ross at GFDL, has implemented explicit tidal boundary conditions. So I'll show you results of what that looks like in a little bit. So we can calculate now tidally varying elevations from elevation and velocity boundary conditions that you can extract from something like TPXO, and it includes included in options, and we have an option to modulate those by the long period tides if that's what you desire. All right, so that's all the lead up to the development that has happened over the last year under this project and a few others. In terms of developing MOM6 as a regional model. I'm going to show you now some implementations of that in the Northwest Atlantic. So we are using this domain. This particular domain is one that myself and my group has had a lot of experience. We have been running this with ROM, so we have a good sense of what that should look like. So it seemed like a good place to start. It's a 7-kilometer model resolution. We are forcing this with reanalysis at the surface and at the site boundary conditions, so both ocean and atmospheric reanalysis, and we're running this in hindcast mode. And I'll show you, so here is an evolution of sea surface height, just to give you a sense of how this is working. And the main thing you can note here is that that you are looking at a piece of ocean that should be recognizable. You see the Gulf Stream path, you see the generation of Gulf Stream rings, the shedding of some of the Gulf of Mexico eddies. Here is a little bit more of eye candy, same domain, same simulation, looking at the vorticity, gives you a nice sense of what the model is capable of doing. It looks very impressive. This is some of our first results with it. With our experience and keen eyes, there's a lot of things that we like about this. And of course, once we start looking at what's happening on the boundaries, there's still room for improvement. But fundamentally, what we can report is that there is a functioning, albeit maybe not the best yet, but fairly advanced stages of regional capability with MOM6. And we can start then with this to start looking at some of the some of the performance of the model. So try to repeat some of the analysis that we have done with ROM simulations with MOM6, and what you see is that the model generally is doing okay, but there's still some areas. So this is, you're looking at the difference between the sea surface temperature computed with MOM6 in this regional domain and OISST. So for a few years, and there are some errors that look very much associated with the path of the Gulf Stream. We are indeed evaluating the Gulf Stream. Here, the dots are showing you the observational path. So this is the 15-degree isotherm, 200 meters, and then you can see that the model is overshooting a little bit. What you're seeing here, the two paths, is one of the things that we really need to come to understand is how the model is behaving with different vertical coordinates. So we have what's called here the HICOM-1 coordinate, which is a combination of isopycnal interior transitioning to a z coordinate, to a geopotential coordinate, and then the pure z star coordinate, which is a shaved cell coordinate. So we see some differences, but overall recognizable. And of course, part of the question is whether this is being controlled by what's happening here at the boundary, and those are questions that remain to be sorted out. Looking at some of the mean features again. So we're looking vertically here at different vertical coordinate implementations with MOM6 and the difference. And here, the first row is sea surface temperature, sea surface height, and mixed layer depth. And again, we are seeing here, for example, in sea surface height, some significant differences around the separation point in Hatteras. And we are trying to track those issues to try to understand how the different coordinate systems are giving us different solutions, and how much of that we can ameliorate by different choices within the model. Eddy kinetic energy, again, is another measure that is helping us diagnose how the model is behaving. And again, this area here just south of the separation of the Gulf Stream is showing up as an area of significant difference between the same implementation with different coordinate systems. So I'm going to skip a few of the slides showing this to make up some time. We have implemented tidal elevations. So this is Andrew Ross at GFDL. Explicit tides into MOM6. And you can see here the first row. So this is two different locations. One is in Atlantic City. One is Apalachicola in Florida. So on the Gulf side. And you see if you're only using the tidal potential that's already built into global MOM6, and then if you're only using the forced boundary as has been implemented as an open boundary condition, and you get a much better solution when you combine both of those. For that, and again, looking at high-speed elevation at both Boston and Atlantic City, you can see that the tidal elevations dynamics are working really, really well with explicit forcing of the tides. Here is the M2 tide, the M2 amplitude. On the left is MOM6, on the right is the TPXO data from which we extracted the boundary conditions for MOM6. So amplitude in the top and phase in the bottom. And similarly for the K1 amplitude, so the two more important tides in the region. So that's another addition to that. Okay, so I'm going to take maybe 2 more minutes to finish up. We have been implementing it mostly in the Northeast Atlantic just because of our experience. There's other regions that are currently in development. Kate Hedstrom is working on an Arctic region, including the sea ice, and we have our NWA model here, and Liz Drenkert at GFDL has been working on implementing a similar model in the Northeast Pacific, including the Bering Sea. Finally, as this is a as this is a new model, it requires new tools, and part of what we've been doing is we've been developing a whole slew of ancillary software that's going to be needed to make this a general purpose useful tool for the community at large. And we started with a grid generation tool that will be available, if not already under GitHub. And this is going to be running as a service, or you could run it on your own local computer if you want. It's all Python based, and you are able to already, if you want, go and sort of draw out your grid that you may want to use a regional domain and set up all your parameters and use your favorite projection, and ultimately download this as a NetCDF grid that then you can use as an input to your model. And ultimately, we will do similar software development for other analysis tools, so generation of initial and boundary conditions, and for post-run analysis. So some final remarks. I think I'm on time. So regional MOM6 is quickly becoming a reality. There's a big community that has joined into this effort. And they're contributing in all kinds of ways, and this is has accelerated significantly over the last year or so with funding from UFS, from the Weather Service, and also from other parts of NOAA, from Climate Office in particular. Most of the desired features that we want to have in a regional high-resolution model have been coded up, and those include the barotropic, baroclinic open boundary conditions, sponge layers, tracer boundary conditions for biogeochemistry, and tides. So that gives us a complete set of tools that we would like to use when we are developing and implementing coastal regional problems. Several implementations are being tested. The Northeast Atlantic, which I showed you today, is the most advanced. But there's significant progress in both the Northeast Pacific, Arctic. There's implementations now in the Indian Ocean and the Eastern Tropical Pacific as well. The community is expanding. NOAA is investing or is pushing for a climate and fisheries initiative that has the potential to really accelerate the development and sustained development of regional ocean modeling, which has been really lacking in the US. Ancillary software is being developed. It's all Python based, and hopefully that will make it easier for people to lower the bar that people need to jump over to get into regional model implementation. And finally, I have a slide that I didn't want to do. As far as UFS, a lot remains to be done. I don't want to jump on this. This is courtesy of Alan Walcroft and Eric Chassinier. The Northeast Atlantic model is the one that we started with because, as I said before, we had a lot of experience with running that particular domain with another model that we were happy with. However, because of MOM6 capabilities and improved computational power, we are planning on taking this model that Eric's group is already implemented in the North Atlantic at 1/12th degree resolution with MOM6, and take a 1/25th version of that that we're going to cut out for the Northwest Atlantic that we then hope to nest within this particular model. So the Northeast Atlantic model that I showed you most of the results from today is really our training grid, and we plan on moving to this type of configurations, hopefully starting this summer and thereafter. So I'm going to finish there, and happy to answer any questions that may arise.
Thank you, Enrique. So we do have a few questions in the questions box. If you can see them, you can feel free to read them and answer.
Let's see, where do I find them?
It's the questions panel on the right. If not, then I can do it.
I don't see it. Oh, let me see questions. Let me see.
Mm-hmm.
I see that, but I don't see the questions.
Okay, no problem. I will read them. So here's one that says, there are the transport observations in the Gulf Stream at, what is this, 26.5 north N by AOML.
Yeah.
Have you done the transport, I guess, comparisons, the transport comparisons between the model and the OBS?
So that's the cable, right? The cable observations. We have not. We have done those with ROMs before. We have not done them with the MOM6 results yet. We've been focusing on other issues right now. But yeah, that's clearly something that will have to be done. Okay.
Also, will open source Python tools integrate closely with leverage other existing projects like X-ray? What is that? XARAY. X-ray.
Yeah, absolutely. Let me see. I don't know. Can you still see my? Yeah. So can you see my presentation?
Yes.
Let's see. So you see, this is all based on X-ray. The idea, yeah. So the grid is an X-ray object. We are using as much of the community through the Pangeo group and other groups that are out there developing really awesome software. We are trying to build into that community, and that's why we moved away from developing a package for MOM6 and rather develop a set of tools that will be independent but easier and more flexible and interface with as much other software that's out there. So yeah, the answer is absolutely.
Okay, and question 2 to that is, does the regional MOM6 with ALE enabled compare with other models in terms of computational cost and performance?
So I'm not sure if the question is, can you do it or have we done it? So yes, of course, you can always do that. And we have done it as well. My personal experience is until today is with, it's mostly with ROMS. It's a regional ocean model. MOM6, for various reasons, compares favorably to that. The time stepping scheme that's implemented in it right now is allowing for time steps that are order 10 times, so 1 order of magnitude larger than what we could do with ROMs. It's not a 10-time improvement because the cost per time step is a little bit higher. But also there's subcycling of the tracer, so that can help significantly if you add biogeochemistry to the story. From what I have seen, it is more than very competitive with other models that I have personally run. But I mean, again, these are things that we are still in full development mode here, right? Once we get down to production simulations, that's where those things will have to be looked at more carefully. But so far, it's been a good experience.
Okay, another one. Could you talk about the reason for the differences in results that you obtained by using different vertical grids?
Yeah. Okay. So, thank you. A bunch of those slides that I skipped over. Here, I'll put this up while I talk about it. Some of it. So here's you looking at, let me see. Let me try to go to some of these, maybe up here. Some of it has to do with our experience in trying to understand what is the right range of parameters from the existing parameterizations that we need to be employing when we're running at these resolutions. This goes back to that comment and that early slide from Bob saying that really the origins of MOM6 is in the climate world. To run this at high resolution, we will have to learn how to do that, and there isn't a lot of experience with that out there in the community, the MOM6 community. So here are some examples where we take, you have looking at mean eddy kinetic energy over a year, and you're looking at different vertical coordinates. Here's the difference between them. But you're also looking in these columns here at different parameterizations, different values for the various parameters for this Bering Sea dissipation, for the boundary layer efficiency, but also there's questions as to how well the open boundary conditions are working with the different vertical coordinates. I'm not convinced that, I'm actually pretty convinced that we haven't solved that problem completely yet. The open boundary conditions seem to be working better for the geopotential style of vertical coordinates. I think that we need to look at a little bit more carefully and how that's working when we have a different type of like the isopycnal interior. So there's a lot of questions and a lot of work that remains to be done with this. Please join us. We could use as much help as we can because there's so much complexity here. So here where you see the wall boundary condition, we just closed it off, right? At some point, we had a hard time understanding whether it is, some of it is due to the different values of the parameterizations, or because of issues with the open boundary conditions that are behaving differently than we expect them with the different vertical coordinates. So you see here that once we closed it off, the errors do seem to decrease significantly. So there's something here, but don't go away altogether. So there's probably a combination of learning how to run the model better at this parameter end of the parameter spectrum, and how we may want to treat the open boundary conditions with the different vertical coordinates. I don't know if that addresses or answers the question.
Okay, well, that was in detail, but I have another one. It says, you offer the OBC tools. Is there any public place we can download, or do I need to contact you?
Those tools are all going to be living out on GitHub. If they're not quite there yet, but as we develop them and test them and make sure that they work correctly, those things will be coming out on GitHub for sure. And that's the way we just like MOM6 is. That's the way we hope to work with the community through that. If you want to get a head start, then yeah, do contact me and we'll work with that. But the grid tools are right now living in some form or another in GitHub, and as the other tools get developed, hopefully over the next year or so, we'll make them available.
Okay. And given the large spatial extent of some of the in-development regional models, are you making plans to have a global set of linked regional models which could feed each other OBCs?
Ooh, plans. That's an interesting question. I mean, my plan, our individual plan for this UFS project that we have is to run the North Atlantic that I showed you with the grid from the Chassinier group, and then take a cutout out of that and increase the resolution towards the Northwest Atlantic. As those simulations come online, they will of course be available to anybody that wants to use them. I don't know that we've ever talked about a global simulation. That's an interesting suggestion. It's a little bit down the line until we feel comfortable with what we have here. So I'm not sure how to answer this. So plan, yes. When, I don't know.
Okay, fair enough. From the operational point of view, how do you choose a vertical coordinate for different domain?
It's again, as we are learning how to run this model at high resolution for a particular domain, that's something. I suspect if my experience with working in different regions of the world with regional models, ocean models, teaches me anything, is that each domain will have its own particular characteristics. So, for example, if you think of the California current has a very narrow shelf and very steep. If you think of the Northwest Atlantic, you have a broad shelf. So you might want to have a different type of vertical coordinate. So you might want to maybe have a transition to a terrain following coordinate, perhaps on the east coast here, Northwest Atlantic, and you might want to think about something a little bit different. I think it's going to be also a question of how long you want your simulations to be. If they are going to be short-lived, so a matter of a few weeks, maybe you might make different choices than if they are going to be, let's say, 50-year kind of integrations where water mass preservation may be more important to you. I don't think that there's an answer. There's a one answer fits all there. It's just going to be a question of whoever is setting up a regional domain in a particular region is going to have to bring their intuition and knowledge of that particular system to bear to ultimately design a workable, it's not just a vertical coordinate, it's also the grid extent, right? That NWA grid served a great purpose for our studies in the Mid-Atlantic Bight. It is not a great grid if you want to study what's happening necessarily in the Gulf of Maine or beyond, right? There's a lot of local knowledge that comes in once you start thinking regionally, and that goes back to the first point I was making, that the global model was designed to work everywhere, but nowhere in particular, right? When you turn this into a regional model, there's different considerations that go in.
Okay, thank you so much, Enrique. We are out of time, as a matter of fact, and thank you very much for this very interesting presentation. If anyone has questions, they can put it on the UFS website, and we will get them directed straight to you. Thanks, everyone, and have a good evening.
Thank you, everybody.
Thank you, Enrique.
Thank you, Enrique. Excellent presentation.
Sorry, I don't know why I couldn't run the presentation mode for my PowerPoint, but whatever, it's okay.
Yeah, it's always surprised sometimes those technology. Thank you. You got a lot of excellent questions. Stacy, is there a way to capture those questions? Maybe we can send to Enrique and Eric.
Yeah,
including the folks asking those questions. They may be interested in knowing those people.
Yeah, I'm happy if you have anything they can forward it to us. I don't see them. I see here the question tab, but it's not showing up. Nothing is showing up.
Can you see the question box? You see the person who asked a question and also the question text?
I see the question box, but there's nothing in it. Nothing is showing up in mine.
Is there a little arrow in a box next to the question pane for you?
Yeah.
And
click the show answer question.
Yeah, that.
I cannot see anything myself. I don't know if I'm.
Yeah, it doesn't show anything. It says.
There is this box you can click under the question. There is this show answered question. Do you see that?
Yeah, but it's empty.
Oh, okay. Maybe let's try this. Can you move them to be a organizer? I guess maybe next time they have to move them to be organizer.
Yeah, because as a panelist, I cannot see it either. I cannot see anything.
Yeah, so here's my main screen, but you're not seeing the. Oh, that's interesting. I don't know. Where you're not
so Erica, can you see the other attendees on the list? We just turn on this.
Okay, now I can see questions. Okay, that's new. Now I can see.
Where do you see them, Eric?
Sorry?
Where do you see them?
Well, it's just appear.
Okay. Eric and let's see.
But I don't know if
Enrique, can you see it now?
And it shows unanswered questions, and I see only one question. Thank you all.
Can you see it now, Enrique?
I cannot. Yeah. Oh, yeah. Now it showed up. Yeah.
Okay.
Can you see all the question? I see only one.
What you do
can
is
see-
click on the box with the arrow pointing up next to the question. On the right side of the box is a box with an arrow pointing up, and it's an X. Click on the box. Can you see the box?
Yeah. Now I can see them, but I couldn't see them before. I don't know if you changed them.
Oh, I see. Okay.
Yeah.
Okay, I see them now too. Okay.
So
What
those
did you change? You made me an organizer or something?
I did. So,
Yeah. Okay. Now as an organizer, I can see them.
Mhm.
Okay.
Okay, now we know that that is how you deal with. Thank you so much.
Stacy, can you save this question box, all those questions?
I
somehow?
don't know how I can get the capabilities to save them.
Yeah, let's figure this out. I think looks like this is useful information to share with speakers, because the folks read the question has a name there. Maybe they want to follow up with you guys. Okay.
Okay, I can take a snapshot. I can email it.
Okay, that would be great.
Okay.
Yeah, we will learn how to do this next time.
Yeah.
Oh.
Thanks for bearing with us.
I know this is.
Oh, I see. Save questions log. Got it. I am going to save the questions. I got that saved. Okay.
All right, perfect. Mm-hmm.
Okay. Well, I'll send you the capture anyway, so there would be a.
Okay. So, Stacy, you can email those questions to Enrique and Eric.
I sure will.
Okay.
Okay.
Right. Well, thank you everybody for the invite.
Absolutely. Thank you for your presentation.
Yeah, thank you.
Okay.
And talk to you soon.
Yeah.
Bye, Eric.
Okay, bye.
Bye.